Good morning and welcome to the 6th presidential lecture. Now we've had 2 biologists, we had 1 physicist, we had a mathematician, and we had a computer scientist. But believe it or not, until today, no chemist has talked to us in this setting. And this is a very bad sign because, you know, as you all know, without the chemists, we wouldn't even know how we are, you know, put together, what the molecules are that make up.
Don't anticipate my talk.
Well, I have planned another 15 minutes. In any case, we all know that there is a periodic system with about 100 plus, and it's getting more. I don't know what there must be an ultimate number, actually. But in the middle of that, there's a very important molecule, and this is carbon. And without carbon, none of us would be sitting here. But carbon also, you know, despite the fact that this is one of the most abundant types of molecules in biology, at least, carbon has, if you use it properly and put it together properly, some very unexpected features. And in the middle of the 80s, there has been a discovery by people that found that C60, so carbon 60, can be put together like a soccer ball called fullerenes. That has been, you know, that caused some excitement and may be also one of the reasons why André Geim and his colleague have subsequently looked at the graphite layers in order to dissect it down to the monomolecular level that they called graphene. And graphene has a whole lot of different features compared to many other, say, structures we have in the living and non-living world. Is it much more, you know, tensile stable than iron, for example? It's much lighter. You can do a whole lot with it. But the disadvantage of André Geim's, say, process was that the monomolecular layer are very diverse in size. Now, here comes Klaus Müllen, who has had a wonderful career in chemistry. He actually has studied chemistry in Cologne, and those of you who understand German will recognize that he comes from Cologne or in the vicinity. He has studied chemistry in Cologne, went to Basel. In Basel, he did his PhD work. He subsequently moved to the ETH Zürich in order to do his postdoctoral time, and then came back to Germany, in this case to Cologne as a professor, subsequently to Mainz as a professor, and in 1989, he was recruited from the local Max Planck Institute to be a Max Planck director. And in this period, he has done numerous discoveries. As I said, he will discuss with us how to put together very precisely, based on benzene, rings, layers of graphene. But his interest, and I'm seeing Guabing Xi here, his interest is much broader. He also is interested in carbon layers that can be used for photovoltaics and numerous other things. So with this, I haven't reached my 15 minutes yet, but I think it's in your interest. Again, Klaus, thank you for coming. I'm very happy to have you here, and we are looking forward to your talk. Give him a good welcome.
Thank you, Peter. Good morning, everyone. Presidential lecture, that sounds very distinguished, even solemn. I don't know whether I can be up to that, but I'll try. Let me first, here, this is when I bring greetings from Mainz. The name of our airport is Frankfurt. This is Mainz in the Rhine Valley, one of the oldest cities in Germany, founded by the Romans as a kind of a defense line against the fiercely fighting German tribes. And here, indeed, I'd like to show you another divide line. Everything in our public discussion connotated with nature, biology, is looked at as beneficial, soft, good for human beings. Everything associated with chemical, synthetic, industrial is looked upon with suspicion, if not fear. Now you may say, yeah, these are the typical prejudices in the public discussion. Let us look at the more and better educated people. Here is one, and the trouble is this book is absolutely worthwhile to read about European history, should you be interested in European history, but look at what this guy Schwanitz says. And I can only say, what the lack of competence, what the lack of recognition. And here, this is therefore my first message. Of course, science and research are part of our culture, and of course, they are basis of all our technologies. But of course, there are limits. And I quote from a famous German philosopher, there are ethical boundaries which we must obey in what we do, my first point. And my second point, as a fundamental researcher, you sometimes have the feeling to look down at application. I think we should take this gap more serious. And admittedly, application does not make fundamental research better. But on the other hand, fundamental research can well be applied. The only point is it is not market or product oriented. In other words, if you would have something useful for human beings and not use it, I think it would be unethical. My third point, that's not a concern for me, frankly. We will hop between fundamental knowledge and function and further on to application in this complex chain of events continuously. But let me indicate a little bit in greater detail what is the impact of chemistry on society. Carbon, nitrogen. Carbon we get, nature gets from carbon dioxide. Nitrogen must undergo some fixation. Oxygen is for free. Now, can chemistry do that? And there was a famous discussion at the Royal Society at the end of the 19th century. Could mankind survive? In view of the fact that the nitrate sources in South America were running out. At that point, the world would have a population of 1-point-something billion. It was that invention, probably the most important invention in chemistry in the last few centuries, which made it possible. So, of course, at room temperature, the equilibrium between nitrogen and hydrogen is very much shifted toward the starting compounds. So that not only required chemistry and physical chemistry, it also needed industry. This is the original plant, and I should just tell you, at that pressure needed and at that temperature needed, 500 degrees, all the metals then available, all the fittings would not work. So it had to be, this is Fritz Haber. This is a plant which you could find now at the Karlsruhe Institute of Technology. It needed a whole set of developments to make it come true. So let me conclude so far. Of course, science and scientific research are the fundament of our technology. Of course, we need to obey ethical boundaries, and of course, it has a tremendous impact on society. Now, would that be sufficient when I'm the first chemist here to convince you that chemistry is a little more than just pouring things together without major accidents? If you accept that, then we can go on, and then I can raise my question. Is the future black? Now, I think you will admit that I'm not talking about all the political and financial crises in the world, all these crazy leaders running mad. But I would like to concentrate on a chemical aspect. And I think we have all good reason to do. Although, if you ask two chemists what is really important for the future, then you are quickly trapped in such a situation. So we need to think a little bit about this in greater detail. And when you look at our societal discussion in technology, there are some key issues in, say, medicine, nanomedicine, in electronics, in handling information, in how we produce, how we perform industrial manufacturing. But I would like to summarize all that into these three areas. But of course, don't believe that I would even try to talk about this or that. But I would like to put that in the middle, and this will be my concern today. Why? Now, let me quote from true authorities. And I have added just here the S. We're living in the materials world. And if you like it a little bit more sound, Eiji Kobayashi, all technologies have their basis in the materials. And now if you take that, then you can quote from Klaus Müllen. If this is true, of course, someone must make them. And why not someone who knows to do it? I mean, I don't know whether every physicist would like it, but that is where material science starts. And by the way, chemistry is the nanoscience per se because by the sheer size of its objects. So this is the second and last take-home information. I think with that I could conclude, but let us go a little bit back again. Isn't it interesting that in history we have been naming a particular area after the most important material? And now I come back to what Peter said. These two elements, silicon, the semiconductor of our times, and the carbon. I would, however, a little bit try to generalize the carbon-containing stuff into the materials, the allotropes, and the polymers. Both built from carbon. And I think you know the word plastic, polymer, from the Greek word, the repetition of elementary units, either in a main chain or as pending side groups. This is what is a polymer. And what we build upon is that a structure can be correlated with a certain function. This is here for the mechanical properties. And you can easily imagine how you produce elasticity or how you produce stiffness. We live upon that correlation of structure and function. You know, when we talk about polymers, there are two different kinds depending on where they occur. A glucose repeat unit, or this is an ethylene built into that chain. Let us take a look at both of them. They occur either as materials, and look, I think you all know them. I think you have seen them, you have used them, or of course as the polymers of life, as the biopolymers. On the other side, isn't it interesting that they all are well known, like superglue or Teflon, they are known under their trade names because they have such a tremendous importance in our daily lives. There is a third group which I must add to that classification. This is, look, there is that represent, you must forgive me that I use the way in which we describe structures by our formula. This is one bond, we call it a single bond, and this is, well, a double bond. And this creates an area of delocalized, highly polarizable electrons. And I can better explain that, again, coming back to what the president has said, that is our building block, and you promise that you are not afraid of that, because this is what we do. We put it into a chain, we make it longer and longer. Why? To create an extended pi conjugation. And this is the reason why organic matter can interact with light, and this is the reason why organic matter can interact with charges. And we will go all the way up, say, to a field effect transistor, how organic matter interact and transport charges. So going back to the synthetic polymer, beneficial or not, of course, on the other hand, polyethylene stands for our society in a good and bad sense. And how could we ignore maritime littering here? Although I claim it is not so much a question of the materials, but a question of education and our societal behavior. And may I add to that, you cannot divide it into the good and bad part. And believe me, and I have some close connection to that problem that ended a very important soccer career. You need ultra-high molecular weight polyethylene, have it hard enough. Of course, you also need to make a polar surface to have the hyaluronic acid move into the gap. But let me conclude that again. It is difficult to separate into the good and bad part of it. We need materials, and let me just give you one idea, and this is why I now go to, again, to the carbon side. What defines the use of a material is its function, but also its accessibility, and if you may take, also the cost. So let us come now to the other side, and I will constantly switch between the carbon-containing polymers and the carbon allotropes. What does that mean? This is a material made from nothing else than carbon. It occurs as a bulk material, such as graphite or diamond. There are, on the other hand, the discrete objects. And there is the monolayer of graphene. Let me just say that I will put more emphasis on that tomorrow, because in all due respect for what Gaiman and Novoselov did on the physics side, it is still a challenge for chemistry, because peeling a graphene layer off for graphite with a Scotch tape has, of course, no importance for an industrial production. So tomorrow I will dare to not only show that as a playground for physics, but also as, in particular, a challenge for synthesis. Of course, you know carbon allotropes, nothing else than carbon, not only as crystalline, highly ordered materials, but as such black junk, carbon black soot, product of incomplete combustion, made in huge amounts. But the fact that the tires of your car live for more than half an hour when you go home is not due to the synthetic rubber, it's due to the addition of a few % of carbon. And something. No, I could not go so far away from my computer here. Second case, carbon nanofibers. You know that there's presently a tremendous interest in lightweight materials which need mechanical reinforcement. Interestingly, at the early 90s, German industry thought that airplane fabrication alone would not justify the immense effort into carbon nanofibers, which of course turned out to be a terribly false forecast in view of what is needed now in all kinds of lightweight fabrication. And let me just add, just a turbine here is not stable enough without lightweight materials. And as you know, of course, the size of the wings here depends very much determines very much the amount of energy which you can harvest. But again, you can only build it with reinforced carbon nanofiber, reinforced material. But let me, you may say that is not our concern. It must be our concern because it's also a matter of price and the chemical development, which I cannot show you in greater detail now, makes it very clear that the materials research, the way in which you fabricate materials, determines all the future market chances. So I will just indicate that you have various ways of doing it. In the future, I will not go too much to our own work, but in case that you might be interested to take a slightly closer look, I will give you some data here. You can make carbon nanofibers from polymers, but also from pitch, which I may want to describe in greater detail tomorrow. The fact that even such a poorly defined stuff as an assembly of polycyclic aromatic hydrocarbons needs supramolecular order in the pyrolysis. Otherwise, you will not have a high degree of graphitization and your carbon yield is disappointingly low. So don't get it wrong. I will not talk to you about black stuff. My question is the future back will, as you later see, have another meaning. But you should be aware that there are a lot of structurally ill-defined carbon allotropes which are of immense technological importance. This is the one I will describe a little bit in greater detail, but again, not so much from the physics but from the chemical viewpoint. And I cannot talk about chemical viewpoint without adding this gentleman. But, okay. You may know him already, but let me tell it that way. I'm quite pleased that your constructions are not yet finished. And I think that tells you everything. Now, as I indicate, we can talk about function. We can talk about price, we can talk about devices, we can talk about integration, but that here is where it all starts. How you make your material available, where you get it from. I look at the materials chemist a little bit like I look at the potter. He needs 3 qualifications. One is, of course, an imagination, to anticipate a complex shape and its function. Of course, a technical skill, secondly. And of course, a raw material. And when we talk about raw materials, then we must think about where does it all start. And at that point, I will now go back again from the carbon materials to the polyolefin, which goes back to the cracker here, where you get the ethylene. This is the lab in Mainz. And this is how you have the polyethylene, then you have the granulated polymer, which you need to process, say, in a thermal process, for example, by extrusion. We'll come back to the availability of the ethylene in a minute, but let me just go back to an issue of the, related to the Max Planck Society. This is Carl Seeger. By the way, he sold the key patent firstly to Mitsui company, one of the key players now in polyolefin, particular polyethylene synthesis. Polyethylene is now made in about 150 million tons in a year. So it's an indispensable material. But on the other hand, Ziegler used, and you are having such a competence in catalysis, he used a combination of titanium and aluminum compounds, which, however, created multi-site reactions, different structures of catalytically active positions. These, the so-called metallocenes or post-metallocenes, again, where Mitsui played a very important role, they are called single-site catalysts. And this is now, yeah, there it works. You start from a cationic site, and this must be designed such that then that incoming ethylene finds a free site, meaning there is always a free site at the catalytic center, and you can insert a fresh monomer, and such the chain grows. And you understand, I believe, why the stereochemistry, I think the word is understandable. For example, the question, where do these groups, such as a methylene group, stand? And this, what we call toxicity, has very important consequences for the thermomechanical behavior of that polymer. So I am pleased that it worked, even if I could not use my own computer. But there is something regarding technology. You do not do that in solution. Because would you do that, and this is a picture which I took myself, when you don't load it on a support, when you don't control particle size, and you cannot process that. Now what we do, we load the catalyst onto a support particle, and we have our tricks there, but this is essential part of the technology. To make the material processable. You could not extrude that. So, in conclusion, the fact that that stuff is so cheap is the result of a very complex nanotechnology. So never again look at it as trivial. You need the right catalyst at the molecular level, but also you need the nanoparticles. And inside these nanoparticles, in that confining geometry, this is where the reaction takes place. And now you could, of course, say, we have a certain amount of raw oil. Does it make sense to make plastics out of that? But look at that. Industry uses about 5%, between 5 and 8% of the oil, and the rest of it is immediately burned without much consideration. So at least I can say from the use of resources, that's absolutely no problem. And if we burn about 90%, why should we not burn it after use? The polymers have a high caloric value. The polymers can be burned. And there is a high technology in that can be done without complications like dioxin and formation. Of course, there are some hidden problems, but in conclusion, what I'd like to emphasize, say, when I show people around at our institute, at the end we talk about recycling. But what I'd like to emphasize, from the technical and chemical viewpoint, all these problems are solved. The issue is our societal decision. Please keep that in mind. Of course, you ask about decomposition. Again, from the choice of the polymer, there is no problem with decomposition. Well, you play either with a lactate, you play with a polyester mixed with some amide. The problem is, of course, when do you tell the material, now you can start to decompose. When you use it like that, it should be stable. This is a problem. The question of stimulus-induced decomposition, this is what we have not yet solved. I'd like to conclude that polymer part with one piece of information, that often we have, of course, a polymer in the solid state, but more often do we have it as small particles dispersed in water. This has so important consequences, first of all, from the aspect of safety, because when you make a polymerization, you release a lot of heat in an aqueous system. This is in a diluted system. This is much more this is much easier. Well, just to explain what you have in milk, let's say a fat droplet dispersed in the water, which you then can destroy mechanically. This is what in polymer synthesis we do with the mice cell here, producing latex particles. And that's about the length scale where we are. And of course, needless to say, two things. First, that there are other nanoparticles where the size determines the properties, and that in polymer science, well, I think it's needless to say that the size, the high surface area per volume, this is the critical issue. And let me just say that the art of doing that in chemistry is not only to have the core of a polymer, also to have the shell. With that, this is a project, a former associate of mine is now professor in Dresden. He's probably the only the only German professor who doesn't speak a word of German, but we have many projects together. Now I can, no. Sorry, that doesn't work, but I told you what defines the use of a material is how you make it. And what unfortunately I cannot show you because my own computer doesn't work here is that you start from graphite as an electrode, you intercalate counter electrodes, counter ions, and you exfoliate. And this is, of course, we have now scaled up to the ton scale. This is, of course, creating mainly monolayers. And then we go into technologies such as batteries. This is, of course, somewhat more practical than using Scotch tape. Electrochemical exfoliation, however, can be described as a kind of top-down approach. We start from the bulk material and go down to the discrete object, the layer. On the other side, here is the reverse. And I will come back to that. The reverse is that we use small units where the raw material is not benzene but methane, and we have the so-called chemical vapor deposition. I think that you have seen that. This is a commercial machine, the Black Magic machine, nothing special. But we make ultra pure, with some tricks, ultra pure graphene, also regarding the charge carrier mobility, which is 500 square centimeters per volt per second. This is good stuff. Bottom up. This is another bottom up. And again, the animation doesn't work. We start with what we heard about from benzenoid species, and then we zip it up, and we do it in a thermal process. And it's easy, but it's efficient, and it can be scaled up. So you will later on see that we start from linear precursors, the zigzag, and go to disc-type precursors. And I am terribly sorry that this cannot be shown because the additional mechanism, that is nice. Now we do it on the surface. We have a monomer, very carefully designed. We put it on the surface from the gas phase. We clean that. There is a diradical, you know that word. It polymerizes, and in UHV, there is nothing to disturb that. We zip it up into a polymer, and I told you, the precursor is non-planar, and then by a heat-induced process, we make the graphenic structure. And I will tell you later that these ribbons are more important than the graphene itself. That is, when you do it on a high Miller index surface, you have them side by side. And let me, however, say that I'm proud to be a chemist, but I can't do without physics. We have good friends and partners. There is one at Empire in Switzerland, Roman Fasel, with whom all that started. I will come to some consequences later, but this is the idea. We make ultra-long polymers. We need, at the end, to have them on a surface. Why don't we
make them on the surface. And the beauty is that we can monitor that by scanning tunneling microscopy in situ. So if you remember what Gerhard Ertl did with carbon monoxide or nickel, in a sense, now you use small organic molecules, you put them on the surface, you activate them, and you control their reactivity. So we had the chemistry from ethylene leading to polyethylene as a result of complex nanotechnology. We use methane or benzenoid species as our access toward graphenic structures. Now, you can look at what I told you from another point of view. This is dimensionality, or should I say, the number of repeat units. You have a chain, polyphenylene, or the polyethylene, or you have a disk, the graphene, you would look at this as two-dimensional. Now, and this is why I like the chemistry of benzene-based design. Now we go to the three-dimensional world. And yeah, polymer chemistry can do a lot, but it can also make tree-like structures, where basically you have continuous branching, and that defines, we have not invented the name, but of course the idea of tree is included in there, the continuous branching going to three-dimensional structure. This is one which we make. It's made, unlike everything in the literature, what? Twisted, tightly packed, interlocked benzene rings. And it should rotate. But you can imagine how that rotates. And since we make perfect nanoparticles, perfect in terms of size, perfect in terms of shape, perfect in terms of the size of the voids, we have absolutely well-defined containers to achieve a nanosite definition when you put in a catalyst, a chromophore, or whatever. This is here one problem. When you have, imagine, a light-emitting diode, where what happens? You have a positive and negative charge meeting, recombining. So at the same area, you have excitons, excited states, and charges. This is disastrous. And by the way, nature in photosynthesis has a way of removing the charge from the photochemically excited states. This is what we do in a dendromer, that we let it combine that three-dimensional particle, and then we move the excitation energy to the inner core by energy transfer, which is an ultra-fast process. First case. Second case. What do we do in chemistry? We look at ensembles, many particles or molecules. But do you learn much? Take a closer look. Do you learn much? But when we look at the single object, we get information not available from the ensemble. And this has led to the invention, and you remember the Nobel Prize for the single, one of them is Stefan Hell, but W.E. Mörner for the single molecule spectroscopy. Here is one case that you need the right object. For example, if you have such a particle where you can control the conditions of a faster resonant energy transfer, you can, in single molecule detection, see, and I will later on, we have not done it ourselves, but I will come back to that and give you a sense of that you have a whole new photophysics. Why? Due to the photophysics as a method, but due to the right materials. Here is another case. You may have in mind that in, I think 2005 in Madrid, there was a bombing of two trains close, yeah, I think it was close to Madrid, at the entrance of into the station. And that compound used there is called TATP, trouble is everyone can make it from hydrogen peroxide and acetone. Problems, and this is, by the way, the reason why you're not supposed to take the liquid on board of a plane, because they want to not take the solid material because it goes off too early. They want to take the two liquid components. The trouble was at that time, there was no sensing. And we have a project with Mainz University that we run an ultra micro balance. And believe me, we have ppb scales, limit of detection, and the response time is seconds, so it's fast enough. Why is this so? I don't want to talk about the basis of sensing, but I want to give you the idea how carbon materials made from twisted benzene rings create an interior, create an inner void for the uptake as a result. The final case is, in principle, the credit goes to, that's funny, my successor, Tanja Weil at our institute. She can do the cell experiments which my group cannot do. I think you know the ceromalbumin as a drug transport, also as the transport vehicle, say, for lipophilic species like acids. I just like, without going into too many details, we make dendrimers which have on the surface patching. That's of course three-dimensional, polar and unpolar species. And these species are water-soluble and go through membranes, and organosoluble. Don't make a membrane nervous. It is the frustration of the solvent shell which qualifies them as unbelievable vehicles. And tomorrow I will talk about the fact that we can then also do gene transfection because we can convince adenoviruses to go into cells. And adenoviruses, the only one, to my knowledge, which are in a, I think, second clinical phase as vehicles for DNA, but they don't go into stem and cancer cells. We can make aggregates between such dendrimers and the adenovirus, and thus also transport DNA. Why? We have the right nanoparticle. This is just indicating that it needs the design, and you know, the type of the molecule makes all the difference regarding the uptake. So, regarding the carbon structure, we start from a three-dimensional precursor, and this is the art of synthesis. And we planarize that. Unfortunately, that doesn't work now. I could show you that this is planarized, and this explains why dendritic precursors are now the source of beautifully designable and perfect graphene structures. The energy technology. We know that problem. Will we run out of sources? My argument is, let's not think along these lines, because let me quote from Stephen Chu, we need better solutions than drilling for more oil and using all the oil sand. Have you ever been to Upper Canada, how it looks like after they have extracted the oil from the sand? Here are the three issues: the saving of energy, the transformation, and the energy storage. But do not forget, nothing is possible without the right materials. That's trivial, of course. Thermal insulation, when we talk about energy saving, but it's nanotechnology, because you need to make ultra-porous material. This is not wrong, since it comes from bus company, that when you have your yogurt in a glass flask, most of what you transport, a major part is the packaging, which is different here. Let me show you a project which I can only indicate and not go into details. 50% of the fuel in an engine is lost to friction, and I don't talk about wear. So we were interested in super lubrication, and the idea is that we use these graphene ribbons, which Akimitsu has made, and this is shifted around without surface reconstruction in an attempt at looking at super lubricity. Let me be very clear. The major credit goes to Shigeki Kawai. He is now at Riken. But in all due modesty, he needs new graphene materials to do that experiment. Do you remember I talked about the chromophores, and here I like to quote one of our papers. This is with W.E. Mönner. This is Daniel Jentsch. This is Long Shen, now for long back in Tianjin. The idea is that we make these chromophores, and I will no longer talk about the single molecule spectroscopy. But there is one chromophore which is strongly absorbing in the near infrared and transparent in the visible. And you put it into a glass laminate. I don't say, yeah, you anyhow produce heat, but you have much ventilation outside. So that's an efficient way of heat management, and it's cheap. It's a nice business, I can tell you. But you need the right absorption characteristics, and you need ultra-high stability. 8 years Arizona conditions and less than 3% loss of the absorption intensity. This is what I told you. When we talk about energy transformation, you would not be able to build such a turbine without carbon nanofibers. Let me go to a totally different area. You know, by the way, under one gentleman at the Max Planck Society, the Max Planck Society has built an institute for, how is it called? Chemical energy conversion. He doesn't even know what he founded, but the idea energy storage on a large scale is not possible in batteries. We need it in energy of compounds, of energy-rich compounds. And for that, we need hydrogen. And I'd just like to mention, our chancellor, as you may know, is a physicist. And I think it could be worse. But she did not tell us where we get the hydrogen from when she advocated electromobility, and she did not tell us where we get the catalyst. Let me show you that, where we get the catalyst for the fuel cells from. The world doesn't have enough platinum to run all the cars on platinum. I'm not talking about price, I'm talking about availability. But we were lucky that, and there were ab initio calculations telling us that when you build graphene with additional sites as nitrogen, that it's catalytically active. I will describe that in greater detail tomorrow. This is hardcore science, but it's useful, and it's superior to platinum. The same holds here. When we talk about energy storage trouble, graphite, which is normally used in a lithium battery, it has a poor, look at that, poor storage capacity. Inorganics are much better, but they have this problem, can you understand? When you put in ions and take them out, they are morphologically not stable. So what we did in our attempt at doing that, we took the best of two worlds. We took a metal particle and, like a piece of candy wrapping up in a sheet of paper, we put it into a graphene shell. And we combined the high capacity with a good morphological stability. So this is a kind of hybrid structure, and it's carbon-based nanoscience. So in conclusion of this energy storage business, whenever you look at processes, you are dealing with energy. Even here, you would not want to produce so much heat. How much energy do we need in cooling? Of course, in lighting, what is it? Charges in, light out. What is it? Light in, charges out. Everything is an issue of efficiency. Storage, how much charge do you get in? How efficiently and how fast do you get it out? But again, it's a matter of the available materials. Now I need to check. He gave a rather long introduction. That is why I must cut a little bit shorter. This is the last chapter, as in case you can survive. Can you do for 10 more minutes?
Yes.
Yeah. I told you the plastic. I told you the nanoparticles. I told you about the energy. Let's talk about the materials. I don't want to give you the impression of an amateur physicist. I don't know enough physics, but I can show you that materials are needed. I think that needs no further explanation. I told you, light in, charge out. Charge in, light out. Field effect transistor, nothing else than a switch. We'll come to that. But of course, silicon is a lousy light emitter, but a beautiful semiconductor. And it's all a question of cost versus performance. Keep that in mind when you're trying to make organic photovoltaics, which I'm not very much in favor. Yeah, well, this is fundamental. It's of course a propaganda argument, but technically we cannot harvest it with organic cells. But of course that our life has changed in terms of displays, there is no doubt about that. But here again, when you look at the color screen of your TV, it's you have the addition of colors to have, but you need pure colors, and it is just a simple design of, if you don't mind, if you have not noticed, I am back at the conjugated carbon-based polymer, but you make that here just by the molecular design that you control the color. Let us briefly go to the field effect transistors. Well, the simplest, no, I thought I should explain a little bit in greater detail. You have a semiconductor between a source and a drain, and you control that current by the field of additional gate. You amplify or you suppress. So again, it is a switch. And the higher the mobility of the charges, the faster you can switch. If I can assume that this is quite clear. In regards to conjugated polymers, you need a high supramolecular order. And that defines the need not only to have a molecular perfection, but also perfection of the supramolecular order. And that defines the importance of processing, the way in which you pass the film. So this is basically what we do with conjugated polymers, where we want a high charge carrier mobility, the faster we can switch, and we want, of course, a high on-off behavior. There is this issue which you all know, which I will not describe in detail, but I just like to mention, and please note, I am not the expert to give answers here, but there are discussions whether a silicon-based CMOS technology may come to an end in view of inherent limitations. So there is, I believe, need for new classes of semiconductors, for sure. This is what we have done. We have no longer made graphene, but so-called graphene nanoribbons. So in a sense, we have made cutouts. And by the way, Akinocha has made them up to 600, even higher micrometer long processors. So the miniaturization business can be solved. We make them either semiconducting, we are trying to make them metallic, but we also can make topological insulators. I will only briefly mention that. So, why you make graphene nanoribbons? You want to maintain the advantage of graphene in terms of high charge carrier mobility, but the graphene has the problem of vanishing bandgap, what you all know, and that means in that switch, the current is never off. So if you're happy with the switch which is never off, you can go ahead. Otherwise, you need to do something. And that has been recognized by the carbon world. So this is why people, like I showed you the carbon nanotube, took high energy radiation and sliced open the carbon nanotube. I wouldn't say it's nonsense. Why not? but it's not defined enough because we have no control of the edge structures, and it needs precision synthesis to do that. And this is what we have done. It is for that reason that we could open, and I will not go into the details, there is no need for that, but I just like in the last few slides to indicate a little bit, again, without either going into the chemical details, nor even making an attempt at talking about the physics, which I anyhow don't understand enough. But let me just give you an idea what you obtain from new materials. This is work following the chemical vapor deposition. You remember what I told you? You need perfect graphene. And Dimitri Toshinovich at our institute, he's moving on now to Duisburg-Essen, applied a terahertz pulse. You know, we have one colleague, that of Misha Bonn, who does terahertz spectroscopy. The issue here, you apply a terahertz pulse and you record a nonlinear optical response in a time domain. You can go up to the 7th order, can you imagine? And the importance is that we have a nonlinear coefficient which is head and shoulders over that of most inorganic materials, because you activate all these background electrons. That means now we can, and you know nonlinear optics in communication technology, we can now work at a repetition rate hitherto inaccessible. First example. The second example, which I unfortunately cannot talk about today, when you look at these ribbons which we make, and we make them perfect, and we make them processable, that you can have them with zigzag states. And at these edges, you have localized electronic states that come with a spin. And that gives you the entry point into no longer injecting electrons into a semiconductor, but also spins. This is also what I would like to mention tomorrow. And here, I think, is an example where I believe the credit needs to go to Lapo Bogani. Let me explain. When we made these, we had beautiful cases of proving edge localized states. We could even calculate that in DFT with Kuhn-Sham orbitals, but the material was not stable under oxygen. And then Lapo suggested to Akimitsu, well, we use your good old solution-made graphene nanoribbons, but we add spin-bearing centers, and there you transfer the spin density, and this is what gives you spins on your semiconductors. And the ESR told us that we have now coherence times in the millisecond range at room temperature. So, we do not want to use ions in an ion trap at a few 0 point something Kelvin. We don't want to use Josephson contact, but we want, on the long run, species with a highly stable phase relation. Before you combine, you have a superposition of qubits. And this is the final case, which, however, make it very clear, we have not done that. There is a lot of theory behind that. Basically, it goes back to the Su Schreiber-Heger theory of polyacetylene, solitons on a polyacetylene. But you need the right materials to make in 2D, no longer in 3D, to make topological insulators. And this is, with that, it's time to conclude. With that, I'd like to conclude. We started from polyethylene and carbon nanofibers, and we ended with topological insulators. So I wanted to make an attempt at showing you the chemistry designed increasing complexity. Of course, we cannot restrict our attention to the molecules, to the bulk materials, because we must also need the processing. We can make a device, but also we need an integration into a more complex system, and they may even include inter-chip, for example, optical inter-chip communication. But it starts with the perfection and the perfect design of a material. And this is why I'd like to conclude by saying that, yeah, this is a chemical challenge. This is a chemical challenge, and it can be solved and has mainly been solved. But of course, the bigger challenge is to make materials which have the potential of opening up new opportunities. Well, when you end a talk, you have to acknowledge that you got some support. What I have not shown today, what I will do tomorrow, is that we have so many partners. Often they play the leading role. The problem with science and materials fabrication are too complicated to solve them in one lab. Collaboration is a matter of competence, but also of a matter of trust. We have been blessed by having found the right partners, whom I think I have given you the names, but I will come to that, back to that in greater detail. Now finally, I am the reporter, or you can say the clown, talking about the stuff. These are the guys who do the work. You may know Mainz is an area in the Rhine Valley where they like wine, and they like soccer, and they like carnival. And so does my group. Okay, this gentleman as well, why not? But let me put it that way. No, I will conclude. I thank them, because when there is nothing to celebrate, they sometimes work very hard. So with that, I'd like to conclude, and I'd like to thank again for this invitation, and you for your kind attention. Thank you. Wonderful.